continuing our coverage of acids and bases, you want to turn to Table M, which is the acid-base indicator table. And so we can make sense of what's going on here at the top of page 21. All right, in general, in reference to these two indicators, which are the most common, you should remember that litmus in acid turns red, and litmus in base turns blue. So there are two kinds of litmus. Easy way to remember that, back in the day when I was a young chemistry student, I remembered red in acid. I also remembered blue in base. And then for phenolphthalein, I want to remember that phenolphthalein in acid is colorless, and that's a long and hard word to spell, so we'll just abbreviate it as pheno. And then phenolphthalein in base is pink. P for the pheno, pink in base. All right, now specifically when you look at Table M, you'll see that litmus has a pH range in which it changes color. And it will say 5.5 to 8.2, and then it will say red to blue. So what they're saying is that at or below a pH of 5.5, the litmus is red, and above 8.2, it turns blue. So why don't we do it this way? From 5.5 and down, the litmus is red. And from 8.2 and up, the litmus is blue. Now students always ask, well, what about in between? Well, in between is where it's changing color. And they rarely ask you about that. Of course, we use indicators. If you recall, you probably used an indicator in an acid-base titration lab. And it was probably phenolphthalein that you used. So let's talk about that. An acid-base titration is, as any titration, is where you're determining quantities with volumes, measured volumes. All right, and typically what you would do in a high school lab, in an acid-base titration, you'll be titrating a strong acid with a strong base. Here's the NaOH, and you would fill up a burette with that. So this would be the burette. This piece of equipment is called a burette. And you'll be adding that sodium hydroxide drop by drop, since there's a valve here that controls a burette, into an Erlenmeyer flask. So you're going to have to know that piece of equipment too. And it's a flask that will allow you to stir the sodium hydroxide as it's added drop by drop on a tabletop with the acid, and it won't spill out the acid when you do that because it has a very wide flat bottom. All right, so what you would have here is the hydrochloric acid with the phenolphthalein, and in this titration what you'll be determining is typically it's the concentration of the HCl would be the unknown. All right, but let's just first of all go over what a neutralization reaction is. A neutralization reaction is always when an acid combines with a base to produce a salt plus water. And the classic example is that of hydrochloric acid plus sodium hydroxide combining to give you sodium chloride aqueous and HOH here, which is water. And I like writing water as HOH because it reminds you how it formed. And so what happened here is any neutralization is a double replacement reaction. The H went with the OH, and the Na switched partners and connected to the Cl. So that's the total equation here. And then if you want to look at the ions that are involved, because remember, HCl is a strong acid, so it really exists as ions in solution, and sodium hydroxide is the same. And so you can understand why the H plus connects with the OH minus, because it's opposites again attracting. And you end up forming water. Now, if you look at this reaction and you eliminate the things that are changing, I should say you should eliminate the things that don't change on both sides, they're called the spectator ions. So what I'm saying is that the Na plus is Na plus here and it's Na plus there, both aqueous, so that's really not changing. And the Cl minus here on the left and the right is not changing. So if you eliminate these spectator ions, what you'll be left with is what we call the net ionic equation. And for any acid-base reaction, the net ionic equation is the H plus from the acid combines with the OH minus from the base to form H12, which is water. All right, now to be neutral, if we're looking for a neutral outcome, and that means for every H plus, there has to be an OH minus. In other words, the moles of H plus have to equal to the moles of OH minus. And from that, we could derive, and I'm sure they did in class, this relationship, which is, since we're getting moles, the molarity of the acid times the volume of the acid would give you the moles of H plus, is equal to the molarity of the base times the volume of the base. So you'll see this in table T under titration. Okay, this is your titration formula. All right, and in this setup here, since they were titrating the HCl with NaOH, the HCl was the unknown. And the typical problem would be worded like this. 35 milliliters of 2.0 molar NaOH are required to neutralize 60 milliliters of HCl. And we know we've come to that point of neutralization because what they do is they add a drop of phenolphthalein to the HCl before the titration begins. And then they'll keep adding the NaOH until they reach a certain color, a pinkish, a light pink color, which indicates we've come to the end point. And sometimes they back titrate that to get more precise, all right? But the idea is continue to add sodium hydroxide until one drop turns light pink. And now here's our question, what is the concentration of the acid? So what you want to do in these problems right away is you want to identify, you want to circle and label who the acid and the base are. Now in this case here, it's the most common acid and base, so it's easy. And so here's your base, the NaOH. And here's your acid, the HCl. So the volume they gave us here must be the VA, the volume of the acid. And the volume here has to be the VB, the volume of the base. And this big M must be the MB, molarity of the base. And that's a simple plug-in of molarity of acid unknown times 60 milliliters equals molarity of base times a volume of 35 milliliters. So I haven't included the units here, but it's important to note you can't mix the volumes. In other words, they both have to be milliliters or they both have to be liters. You can't have milliliters on one side and liters on the other. All right, and then the math is real simple. And here, just to practice, since we had two significant figures in the weakest link, your final answer becomes 1.2 molar. So that's a typical titration problem. And we'll do some of these later when we do the questions part of this unit. Also, you want to note, in this case, we were adding base to acid. So that means the pH would steadily increase until it reached a pH of 7. Because whenever you titrate a strong acid with a strong base, which is what HCl and NaOH are, the end point is a pH of 7. All right, so when you add base to acid, the pH increases. And of course the opposite is true too. You could flip this around and have the NaOH is your unknown, and you could add HCl to NaOH. All right, the one that is the known concentration would be called a standard in a titration. All right, so that's good terminology to write down too. Standard. When they refer to the standard, what they mean that it's the known concentration. It can either be an acid or a base, whichever one is known, is the standard that we're going to use to figure out the unknown. Okay. Then towards the bottom of this page, the last third of this page, we'll spend a little time, not sure if you covered it in class, but it still is part of the New York State syllabus. We'll spend a little time on what is called the alternate theory. You see, everything that we've done up until this point, and I think I didn't mention that on the previous page, is the Arrhenius theory. And Arrhenius is the one who tells us that acids produce H plus and bases produce hydroxide ions in water. But there's another theory, in fact there's three theories on acid-base behavior, but the other theory you need to know is something called the bronsted-lowery, or the alternate theory of acid-base behavior. Now, in this case, they define acids and bases a little differently. It's a broader definition. So in this case, an acid is a substance that donates hydrogen ions, and a base is a substance that accepts, well, the word species I think is better than substance, that accepts hydrogen ions. Or another way of saying it is acids lose H plus and bases gain H plus. So from this view, or this theory, sees acid-base reactions as involving the transfer of hydrogen ions, which are also known as protons. All right, so for example, if we look at NH3 in water, and this will help us to explain, maybe you remember I had said in table L, the bottom of table L, there's a weak base, ammonia, that's also known as ammonium hydroxide. How does ammonia produce hydroxide ions? Well, the alternate theory helps us to understand that. Excuse me, let me just drink a little water here. So what happens here is the NH3 combines with the water, and the reaction involves the transfer of a proton. So watch what happens. The NH3 ends up gaining a proton from the water, so NH3 becomes NH4, and because the water has lost or donated a proton, we'll label the water, relatively speaking, as the acid. All right, we'll label the NH3 that gains the proton as the base. All right, again, this doesn't mean that water has a pH less than 7. What we mean is relative to NH3, compared to NH3, the H2O is more willing to donate a proton than to accept a proton. So once again, we should note that here, that an H plus hydrogen ion is also known as a proton. And that's because, if you recall, a hydrogen atom is a proton and an electron. And H plus means, going back to your bonding, going back to ions, it means it has lost its electron. So if an atom that consists of only a proton and electron loses its electron, then what you're left with is a proton. So hydrogen ion is a proton. All right, so now let's look at this reaction here. Let's just also emphasize it's a relative thing. Look what's happening here. In this case, the HCl combines with the water and it forms H3O+. So the HCl, in this case, is donating a proton to the H2O. The H2O is accepting a proton, and therefore the H2O relative to the HCl is the base, according to these definitions, and the HCl is the acid. And the other thing about this alternate theory is that we emphasize the reversibility of acid-base reactions. So in the forward direction, there will be an acid and a base. And in the reverse direction, you'll get the conjugates, the things that are formed, which are acids and bases. So every acid has a base, and every base has an acid. I'll show you what I mean. Let's look at this example here, where I said try these. Okay. NH3 is coupled with NH2. These are the conjugates. You notice they differ by 1 H. And for the NH3 to become an NH2, it would have to lose an H. So if it's losing an H, that means the NH3 is acting as an acid, and its conjugate on the opposite side, in the reverse, would act as a base. And so that leaves us with O negative 2 and OH minus. Notice the O negative 2 is becoming an OH. So it's gaining an H, and naturally it's acting as a base, and so its conjugate on the opposite side in the reverse direction would be acting as an acid. And that's kind of weird to label the OH as an acid, because according to Arrhenius theory, hydroxide ions are associated with bases. But again, this is a relative definition, so don't let that disturb you. Now, okay, why don't you try the next one here on the right, and you should start by labeling the conjugates, and that is species that differ by 1 H. Notice the F and the HF are conjugates. And that leaves the H2S and the HS minus to be conjugates. And then ask yourself, for F minus to become HF, is it gaining or losing an H? So clearly it's gaining an H, so that means the F minus is your base. And its conjugate on the opposite side has to be an acid. And that leaves the H2S and the HS minus to be acid and base. Now don't try to memorize a sequence here that it always has to be A, B, BA. But what you should know is that you'll always end up in these reactions with 2 acids and 2 bases, and 1 on each side. All right, and finally this point about amphiprotic. An amphiprotic species is like the word amphibian, like a frog can live on land and water. Amphi means can do both. So an amphiprotic or amphiteric substance or species is something that can gain or lose H+. And water would be a good example of that here. Notice how the H2O can become OH minus, or the H2O can become H3O plus. In order for something to be able to gain or lose an H+, though, it has to have at least 1 H. So if they were to ask you, which of the following is amphiprotic? CO3 negative 2, O negative 2, HSO4 minus, or N negative 3, you see what I mean? The HSO4 minus, having at least 1 H, can either lose that H or gain an H, but the others cannot. So the answer would be the HSO4 minus alone can be amphiprotic. All right, so now let's turn our attention to doing some problems on acids and bases. You can take a break here, or go right to that ahead of me, and I'll catch up to you.